to see the first of Maxwell equations in the dielectric material. This would be the electrostatic equations for dielectrics. Here we have our parallel capacitor plate. This is Q negative, Q plus, and in the previous video we find that if there is a non-uniform electric field, the divergence of it, or the divergence of the polarization, that is the electric dipole moment per volume, the divergence of it is the same as the charge density. Charge density of the charge that are induced here in this dielectric, it will be charge induced. So here we have the density of these charges that are induced, or the charge density of the polarized charges, but usually this, that is density and has units of coulombs per volume, this is called the charge polarization. But here we need to be careful and not to think that this is a charge and think that this is in units of coulomb. No, this is a density that is called the charge polarization. So right, we have this equation. We have that in another video we find the Maxwell differential equation, the first one, that is the Gauss law of electricity, that is that the divergence of the electric field is equal to the density, rho density, divided by epsilon naught. This density refers to all the densities in the dielectric. But we will divide this into the density, that is the polarized charge, and the rest. So we have that the divergence of the electric field is equal to, let's call it rho free, minus, well, plus the density, but has a negative sign, so minus the charge polarization divided by epsilon naught. But this is the same as the divergence of the electric dipole moment, so we have free density minus the divergence of the electric dipole moment per volume divided by epsilon naught. In the previous video we saw that the electric dipole moment per volume is proportional to a constant C times epsilon naught times the electric field, so free electric field. So here we have that the divergence of the electric field is equal to rho free minus well, let me put first, let me solve first for this part. So rho free divided by epsilon naught is equal to the divergence of the electric field minus plus the divergence of the electric dipole moment per volume. So we have that this is the same as the divergence of the electric field plus the electric dipole moment per volume. So now we replace this by this. So here we have C epsilon naught E free. So we have that the free charge density divided by epsilon naught is equal to the divergence of epsilon, here's divergence of epsilon of electric field, free electric field, or the electric field that was before the electric, times 1 plus yeah, see here I forgot to divide it by epsilon naught. divided by epsilon naught. That happened. So here I have 1 plus x and the electric dipole moment. X electric field. No, the electric field is just x. 1 plus x, and 1 plus x is the K constant or the dielectric constant. So we have that the free charge density divided by epsilon naught is equal to the divergence of the electric field times the constant. The general form is to put the constant inside the parentheses, so we are taking the divergence of all this because sometimes this constant could be changed, so it is not a constant. But if K is constant, we can just write it as the divergence of the K times the divergence of the electric field here K. But this is the general form. This is the first of the equations for the dielectric. The second remains the same, that is the curl or the circulation of the electric field is 0, and for the dielectric will be the same. We put a K here, we put 0. Before putting the dielectric, we can write it as the curl of the electric field. Here we can put a subnode, that just means that is the electric field before the electric, and this is equal to 0. So if we have this and this is the electric field after the electric, that is this the same. And then we would have that the both curls are the same 0, and we can equate them, and so we have that the electric field, or here the electric field times some constant, is equal the electric field before the dielectric times the constant is equal to the new electric field. So or we can say that the electric field before is equal to the electric field after divided by some constant. So actually the new electric field is decreasing by a factor of K, and because the voltage is the integral of the electric field dot the L, or the distance, and this is decreasing by a factor of K, this would be decreasing also by a factor of K, and because capacitance is the charge per voltage, then the capacitance will increase by a factor of K, as we saw on other video. So we have this equation and this equation, the capacitance, we already saw it, and alright. Now for the electric field, we have electric field is equal to the charge density, surface charge density, that is Q times the Q divided by area, and then this by epsilon naught.